All right.
I think that they just got a really awesome calculator. Darker later. First of all, to actually even open technically
Okay, I guess we can get going here. So just some administrative stuff. Exam 3 on the schedule is set for November 26th. And I talked about moving that, right? So we had said the 14th, that's a Thursday. Is that what we want to do? We can do the 19th also, which would be a Tuesday. What do y'all think? Oh, wait, the drop date, we were doing off the drop date, that's right. Yeah, drop date, so the 14th. Let's just make it the 14th then. So this is going to be officially the 14th. And it will cover up through 4.4. Okay, so through and including 4.4. Wherever our last one stopped. So, yeah, related rates, 2.7 all the way through to 4.4. All right? Okay, now, I do have a quiz, but again, I think what I'm going to do is let's get through the lecture first, and then hopefully at the end, there will be time for that quiz. I want to give you like 15 minutes for it. So I don't know if I can ask you to remind me, because I don't know if you will, but say about 2:25-ish, maybe 2:25, we'll try and stop. Okay, so last class, what we were doing was talking about how to find the max and min of a function on a closed interval, yes? Okay, we are going to just kind of take all this idea of finding max and mins and just back burner it just for a moment and cover this section. This section really could be put at the end of the chapter. We could do it separately, but in the book, this is the next section. And it deals with what's called the mean value theorem, which is actually a really important theorem in mathematics. And what's nice about the theorem is that it's easy to visualize. And some of the repercussions of it, or some of the consequences of this theorem are kind of amazing. And I'm going to give you an example, and we're gonna see if you find that it's amazing also, okay? So first of all, to get to the mean value theorem, which we will abbreviate MVT from now on, we first start with another theorem, which is called Rolle's theorem. And Rolle's theorem, I think most students have no problem understanding Rolle's theorem. Here's a bunch of stuff, but let me just get to the picture. Here's what Rolle's theorem says. It says, let's say you have a continuous function on a closed interval, all right? So we have a function, it's defined on a closed interval, it's continuous, I can draw it without picking up my pencil, and it's differentiable. Now this is something that we have not talked about with the previous section. We're saying we want a function that's defined on a closed interval, that's continuous and differentiable, meaning that the derivative exists everywhere in here. So we can't have a corner or a cusp, all right? And obviously we can't have a jump, because if we have a jump, it wouldn't be continuous anyway. But any function that is continuous on a closed interval and differentiable on the interval, then then we have the, the following. And let's just see if this makes sense to you. Let's say when we plug in a to the function, we get a value, right? A y value. And let's say we get the exact same value at the end of the function. So the y coordinates are the same at the endpoints. And then we connect it with a continuous differentiable curve. Rolle's theorem says that somewhere within the function, somewhere on that red function, when you look at the slope of the tangent line, it has to be equal to the slope of the line connecting the two endpoints. So what is the slope of the line connecting these two endpoints right now? It's 0 because the two endpoints had the same values, right? So we know the slope of this line is 0. Rolle's theorem says somewhere in here, you've got to have a tangent line that has a slope of 0 also. Does it make sense that that would be true? Okay, let's look at a different example. Okay, so look at that one. Okay, another continuous curve between two endpoints, right? And differentiable, no corners or cusps. Somewhere in here, we should get a slope of a tangent line that is equal to the slope of that line. So in other words, 0, right? And can y'all see where it happens? There's actually two places, right? It happens here and here, right? Rolle's theorem says those points are guaranteed. We're going to have at least one. You could have more than one, like in this example, but one of them you have to have at least one point. Here, a last example. How about that one? So what's the slope of the line connecting these 2 points? 0. And what point in here would also have that same, every point, right? So you go to any point here, the slope of the tangent line is actually still 0. So that's an example where we have an infinite number of points that have the same slope tangent. So we've had an example with 1 point, 2 points, and now an infinite number. So let's go back up and read Rolle's theorem now. Okay, let's read it. Rolle's theorem says, let f be a function such that 1, it's continuous on a closed interval. 2, it's differentiable on, you don't even need differentiability at the endpoints. You just need it within the interval. So as long as we don't have corners or cusps. And make it so that the two endpoints have the same value. Then the theorem says, then there exists some number c somewhere inside the interval, somewhere in the interval, such that the derivative at that point is 0, which is equal to the difference of the y coordinates. Does that all make sense now that we've seen the visual? Okay, so going back to this, I'm going to go to that first example again. Rolle's theorem says that there must be some, like if this is A here, right, and this is B here, there must exist somewhere inside of A and B. Not at A, not at B, somewhere inside, there must be some value C that when I go up to the function, I look at the slope of the tangent line there, it's going to be equal to 0, which is the slope of the line connecting those two endpoints. Okay? The main thing I want you to take away from this, because it seems like I've repeated myself like 4 times now, is that the C that is guaranteed by the theorem is somewhere inside, this means element of AB. So C is an element of AB. That means it's inside the interval, not at the endpoints. Okay? All right. So that's Rolle's theorem. That's not the mean value theorem. Let's take a look at the mean value theorem. Okay, let's look at the theorem first, and let's see without a picture if we can make sense out of it. The mean value theorem says, let f be a function such that, first, it's continuous on a closed interval, right? So we can draw it without picking up our pencil. Same thing as Rolle's theorem. It's differentiable on the interior of AB, so no corners or cusps. Same thing as Rolle's theorem, right? And then it says, then there exists a number C inside A and B, right? Such that this, now that's really small, so I'll put it up here. Such that f prime of C is equal to f of B minus f of A over B minus A. So can you tell, just by looking at this, what's different from Rolle's theorem in this theorem? Like what does Rolle's theorem have that this one doesn't? F of A equals f of B. So remember on Rolle's theorem, the condition was that the two endpoints had to be equal? And that's why you could get a flat line and then you'd have, a tangent would have to also be that. The mean value theorem does not have that condition. It doesn't have the condition that the two endpoints have to be the same. But it's also not saying that the derivative has to be 0 either. It's saying that the derivative has to be equal to this. Now we'll make sense out of that in a second, but let's take a look at this. So here's Rolle's theorem, right? Here's Rolle's theorem. Endpoints are the same. We know that somewhere in there you got to have a slope of a tangent line that's also going to be 0. The mean value theorem takes this idea and says, what if we were to rotate the function like that, and now you have not the same endpoints, right? But what we can say is that between these two lines, right? Between these 2 points, there is a secant line, right? And somewhere between A and B, there has to be a C somewhere where when we go up to the function, the tangent line is not going to be 0, it's going to be what? Parallel to that line connecting those two endpoints. Do y'all see that? Okay, so the slope of the tangent line, the derivative here at this point C, has to be equal to the slope of this line. So what's the slope of this line? Rise over run, right? Rise over run. The rise is what? The difference of the y coordinates, f of b minus f of a, and the run is the difference between the x coordinates, which is b minus a. So it's essentially the same formula, just now we're kind of twisting it, all right? Does that make sense that would be that theorem would still apply? So again, Rolle's theorem, mean value theorem. Rolle's theorem, mean value theorem. Got it? Okay. Now, let's do an example. These are weird problems when you see them in your homework, okay? Here's the way they'll be worded. Verify the mean value theorem for f of x equals, let's say, I'm going to give you a function, square root of x on the interval 0, 1. I'm convinced that what's happening is that the people who come and clean the rooms at night are taking all these used markers and putting them back into our office area and making it look like brand new markers, and then we grab them and we bring them back in here and they don't work, they're all dead. Because a new marker should look better than that. All right, so we're supposed to verify the mean value theorem for this function on this interval. So in order to use the mean value theorem, we must have a continuous function on a closed interval. Is this a continuous function? As long as you're on its domain, right? So you can't have negatives in here. You can have 0, but you can't have negatives. And we're looking between 0 and 1. So this is a continuous function on that interval. So we got that. Is it differentiable? Because we have to have differentiability. So maybe we should take the derivative real quick and just take a look at the derivative, make sure that it doesn't have any problems. Okay, so what about the derivative of this? 1 over 2 root x, right? Okay, so when you look at that derivative, is that derivative, go ahead, was that a question?
Well, I was just going to say that now it equals 1 over 0.
Yeah, you can have 0 now, right? But the theorem said we only had to have differentiability on the open interval. So if you go back up and look at the theorem here, must be continuous on a closed interval and differentiable on the interior of that interval. So for this particular problem, I just need that thing to exist on this interval. So does it exist here? This says I can't plug in 0, right? And 0 is the only place that we would have a problem here. So we are still good, right? Still good. All right, so the mean value theorem says, by the mean value theorem, there exists a C in the interval 0, 1 such that f prime of C is equal to f of B minus f of A over B minus A. The slope of the tangent line must be equal to the slope of the, what do we call that line? This is the tangent line at a point, right? This is the secant line connecting the two endpoints of the curve, right? So mean value theorem says there must be somewhere where the slope of the tangent line to the curve must be equal to the slope of the secant line connecting the two endpoints of the curve, all right? And our goal now is to go find the C. We have to go figure out what the C value is that makes this true, all right? So now let's just start working with this. I'm going to start working with this right here. Okay, so I'm going to take this equation, I'm going to work the left side and right side of it down. What is the derivative of our function at C? Well, that's the derivative of our function, right? So if I say what's that function's value at C, you would put 1 over 2 root C, right? Okay, that must equal the function's value at B. That's the function's value where? At 1. Minus the function's value at 0 over B minus A, so 1 minus 0, right? Okay, so now what we do is we have to figure out, what's f of 1, what's f of 0, what's 1 minus 0. So what's f of 1? Where are we plugging 1 into? The original function, right? So this is going to be 1 over 2 root C must equal the square root of 1 minus the square root of 0 over 1. And that's just 1 on the right side, isn't it? Just plugging in. So this means 1 over 2 root C must be 1. And now we just have to solve this for C. So to solve this for C, I'll multiply both sides by 2 root C. I'll divide both sides by 2. And last step, square both sides. And remember, when you square both sides of an equation, you do not have to do plus or minus. When you square root, you do, right? Okay, but when we square both sides, we are supposed to check our answer, aren't we? So, but we can check this. 1/4, if you plug in, this will be true, all right? Okay, so that's it. This is it. We have verified the mean value theorem. Have we found a number inside that interval where the derivative at that value is equal to the slope of the secant line? We have. It happens at 1/4. Okay, so visually, what this means is if I graph this function, what's going on? Come on, wake up. So if I graph this function, square root of x, and I do this on 0 less than or equal to x less than or equal to 1, right? If we look at that function right there, there it is. Then if I go to the value on this curve of, 1/4, which is 0.25? Somewhere around, I don't know. I had it right there. Okay, at that point right there. All right, so if I go there, what was it, right there? And I take the slope of the tangent line there, that should be equal to the slope of the secant line connecting the two endpoints of the curve. All right? Does that make sense? Should I work through another example, or do you think you could do one? I don't mind doing another one, but it's the process is the same for each one. Take the derivative, make sure it exists on the interior. You set up this equation, you work through the algebra, solve the equation for C. One more? One more? Okay. All right, so let's do something a little more interesting. All right, so for the next one, let's do x plus 1 over x squared plus 1 on the interval 0, 2. Okay, I'm not quite sure. I'm just making up this problem, all right? So I'm not quite sure where we're headed with this. I hope we can do the algebra involved. I think we'll be able to. We'll see. All right, so let me think about this. Hold on. Do we really want this? You know what? I wouldn't do that to you on a test. So let me do it. Let me do this. Change that to an x, and let's just make that down here minus 4. Okay. It's a little bit easier to work with. All right, x minus 4 on the bottom. All right. So first of all, are we dealing with a continuous function on this closed interval? Yeah, we do have a problem with this function at 4, but that's not in our interval, so we're good to go, right? All right, so we need to take the derivative, make sure that it is okay on that interval. So let's take a look at the derivative. So we go quotient rule here. Derivative of the top is 1 times the bottom minus the derivative of the bottom, which is 1, times the top. All over the bottom, squared. Okay, I can clean this up a little bit. If I clean that up, I think I get negative 5 over x minus 4, that quantity squared. Okay, so that's our derivative. Is this derivative valid on the inside of this? Yeah, because again, this will only have a problem at 4, which is outside that interval. So this on that open interval is checked. We're good to go on there. All right, so what does the mean value theorem say? The mean value theorem says that there exists a c somewhere inside that interval 0, 2, where the derivative at that value c is equal to the slope of the secant line, right? So this you would write down every single time. Okay, there we go. So this is what the mean value theorem states. It's our task now to go find the c that makes this true. Because we know what a and b are, right? And we know what the derivative is. So what does the left side turn into here? Negative 5 over c minus 4, that quantity squared. That must equal, okay, f of 2 minus f of 0 over 2 minus 0. Slope of the tangent line at c, slope of the secant line connecting the endpoints. Let's just fill in, you know, what's f of 2, what's f of 0. Let's do our little arithmetic on the denominator. So what is f of 2? So if we plug 2 into the original function, we get 3 over negative 2, so negative 3 halves. Minus, now what happens if we plug in 0? Be careful here. Plug 0 into the original function. You get 1 over negative 4, which is negative 1/4. But we're subtracting it, right? So be careful with that. That's subtracting negative 1/4. And then here we're going to have 2 on the bottom, right? Okay. Let's continue that over here. What does this numerator become? Positive, negative. Well, this is going to be positive, right? So I'll just write down. We have negative 5 over c c minus 4 squared equals negative 3/2 plus a fourth all over 2. Right, that's what this is. Now, what's negative 3/2 plus a fourth? Negative 5/4. Yes? Okay, that right side, negative 5/4 divided by 2, is really negative 5/4. I'm sorry, is it really negative 5 what? 8ths. So just rewrite that 2 as a 2 over 1, and then flip like reciprocal, right? Okay, now you get to solve that equation for C. So why don't we do, you can do like a cross multiply if you want. Or you can just look at this. Look, since the numerators are exactly the same, right? They're both negative 5s. That means for those to be equal, the denominators would have to be exactly the same, wouldn't they?
Yeah.
Right? So essentially, you can just go straight to this, which is the same thing you get if you cross multiplied and then divided through by negative 5, you'd get that same equation. Okay, how am I going to solve that? I could do square root on both sides right now. Now, when I do square root, I have to do plus or minus root 8. And the last step to get C by itself, add 4 to both sides. All right. Looks like we have 2 answers. 4 plus root 8 and 4 minus root 8. The mean value theorem says we have to have at least one answer in this interval, right? One of those, I believe, is not in the interval, right? If you do 4 plus root 8, you're going to be outside the interval. What's 4 minus root 8? So 4 plus root 8, that's definitely bigger than 2, so that's no go. 4 minus root 8, you can check on your calculator. Square root of 8 is like 2 point something. So 4 minus 2 point something is going to be within that interval. So this is it right here. That's our answer. So on your homework problems for this, you're going to just have to mess with different sorts of algebra at the end to solve for C. So this was x plus 1 over x minus 4. And we are looking at 0 to 2. Okay, so that's our function, if y'all can see that. So the slope of the secant line connecting here to here, there's, we have to go to, I don't know what the value is, 4 minus root 8, but it's somewhere around in here where the slope of the tangent line would be equal. Make sense? Okay. All right, that's all great, you know, wonderful. But how is this useful? Because I would argue this doesn't seem very useful. Would you agree? Like, what's useful about this? Okay, so let's take a look at a problem that we had a while back. We looked at a problem, I believe this was it. It was show that cosine x equals x has a solution on the interval 0, 1. Okay. We did this, I want to say months ago, when we were covering something called the intermediate value theorem. The intermediate value theorem said that, not the mean value theorem, the intermediate value theorem said that if you have a continuous function and you want to go from some point with that continuous function to some other point, then whatever y values you have here, okay, whatever y values you have, you must go through every value in between. So if you pick something in here, whatever you want, it's guaranteed that there's some value in here that would spit out that answer. Does this look at all familiar? I don't want to bring it up again, but I mean, like bring up the notes from it. But the way we showed that this had a solution on this interval is what we did is we brought everything to one side. And then we said, hey, look, this right here can be looked at as a function being set equal to 0, which means we really are trying to find the x-intercepts, right, of this function right here. So what we did is we said, all right, let's look at what that function's value is at the left end point. So what would happen if I plug 0 into this as a function? Cosine of 0 is 1, and then minus 0, so you get 1 here, right? Do you remember what I did next? Plug 1 in, right? So if we plug 1 in, we get cosine of 1 minus 1, right? And if you go into your calculator and you are in radian mode, not degree mode, and you do cosine of 1 minus 1, you're going to get a negative answer. Negative. And so what did that tell us? It has to pass through 0, right? So it's like what we know about the function is that at 0 it's 1, right? And at 1 it's negative, right? I don't care where it is. So we would say, since cosine x minus x is continuous, it must pass through every value between 1 and a negative number, which includes 0, right? 0 is in there. So it must satisfy that equation at some point. I don't know where yet, right? And we weren't able to find where. We just were able to say it has a solution there. And so all you had to do was use the intermediate value theorem, show that you went from positive to negative, or if it's a different function, maybe you go from negative to positive. Anytime you have that switch in signs, you know that you pass through 0, right? Okay, so I'm going to change this problem a little bit. I'm going to say, show that cosine x minus x has exactly one solution on that interval. Okay, I'm modifying the problem. I want us to show that it has just one answer. See, because what we do know is that this goes from positive to negative, right? But what stops it from doing this, like, you know, and passing through and hitting the x-axis a bunch of times and just winding up down here? We know that there's at least one answer, right? One answer? Okay, so this is connected to the mean value theorem, but not really. We actually don't need the mean value theorem for this. But I want to see if anyone can figure out how we can show this, that it has only one answer. Don't be thinking mean value theorem, all right? Don't. This can be done without it. So we already know that there's at least one answer, right? I want us to show there's exactly one. We don't know anything about the middle of this graph, do we? We don't know anything. All we know is that it starts here, starts at a positive number, and ends at a negative number. So we know that there's at least one x-intercept in here, right? At least one. Could be more than one. I want us to show that there is only one. So let me try and help y'all out. Unless you have, I'll give any last minute. Go ahead, Al.
You can kind of choose a number between those two numbers between those two.
Uh-huh. Test again to see plus or minus. Okay, so you're suggesting that I pick another number and check for positive or negative, right? And let's say I pick this number in the middle and it turns out to be negative. Then I would know that I have what? At least one answer in here, right? But what if I pick this number and it turns out to be positive? Does that mean I don't have an answer between there? No, it doesn't mean I don't, because it could have done this, right? So you still could have missed 2 or 3 or something, right? If we do get a change in sign, we know there's at least one answer. If we don't get a change in sign, there still might be. Okay, so let me try something else. Okay. watch very carefully as I draw. Think about the function I'm drawing and think about the derivative, the slope of the tangent line as I draw this. If it has one solution, right, looks something like that. If it had one answer, okay, let me draw another picture. What would it look like if it had two answers, two x-intercepts? I would have to go, what, down, right, across, and then I would have to do what? I'd have to go back up, and then eventually I would have to come back down, right? So think about the derivative. When you look at this right now, what's the slope of the tangent line here? Let's say 0, right? As I head to that point, what's the slope of the tangent line? Negative, 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 and I get there, right? Here, what happens? Slope of tangent line, negative, 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 negative. But to get back up, what do I have to do? My derivative is going to have to change back to being positive. There's a change in the derivative from going from a negative to a positive. Do y'all see that? This is fundamental, especially in the next section. So let's just take a quick look at this derivative, okay? Let's just take a look at the derivative of this function right here. What would the derivative of that be? So what would f prime of x be? It would be negative sine of x minus 1, right? That's the derivative of this right here. And what can you tell me about that derivative? It's what?
Negative.
It's always negative. Well, it could be 0. When would it be 0? Think about this right here. Sine, the sine function by itself. Forget the net minus 1. Sine is always between what two numbers? Negative 1 and 1, right? So let's say this is positive 1. Minus 1 would be negative 2. That's a negative number, right? Okay, what's the other extreme? What if this was negative 1? Then what would you have? Negative 1 minus negative 1 would be positive 1. And then you get 0, right? So the only extreme case I could have here is if this was ever negative 1. But where does that happen? When is sine negative 1? At 3 pi over 2, right? 3 pi over 2. Look at the interval we're looking in, between 0 and 1. So what we can say is in this interval, do you all agree that this is always going to be what? Positive, right? This right here will always be positive between 0 and 1. And then you throw a negative in front of it, and now it's negative, right? So all of it together is negative. And then you subtract 1, so you're going to get a negative number. So let's recap what we're saying. In the beginning, using the intermediate value theorem, we said, look, between 0 and 1, we have a change in sign. It goes from positive to negative. And then we said, let's take a look at the derivative, and we know that the derivative is always negative in this interval, which means my function is always going down, right? Always going down, because the derivative is negative. So I can only cross through the x-axis one time. The only way I could have more than one x-intercept is if I turned back up, right? But then my derivative would have to be positive. But it's impossible for it to be positive on that interval. So we're done. It's a hard, I mean, it's not like solving an equation where you get the answer at the end and you box it. You have to first use the intermediate value theorem to show a change in sign, and then you have to look at the derivative and show that it's always negative. And then you can conclude that there's only one x-intercept. What? What? Do you agree that if I say the derivative is negative, that the function is going down? Okay? And do you agree that the only way you can get from here to here, right? If I say you have to always draw and always be going down as you draw from left to right, means that you're going to cross through the x-axis only one time. Because in order to come back up and have a second x-intercept, your derivative would have to change from negative to positive. But it can't. It always has to be negative. So it's impossible for your graph to ever start turning back upward. Within the interval. Now, later on it does, okay, but, well, the most it ever does is gets to 0, but. I'll graph cosine of x minus x. It's an interesting function. I'm just going to graph the whole thing. Cosine x minus x. It's like it wants to be a cosine function. It wants to do this, but the subtraction of x on it just keeps on making it go down and down. So look, it's always decreasing, right? So this function is always going down. So we were looking for the x-intercept in here, and we found it. Well, we found that there's only one, right? Between 0 and 1, here's 1. Between 0 and 1, it was positive, then it was negative, and the derivative in there has to be negative, so it's always going down. One x-intercept, done. So, moral of the story, you can actually, with the intermediate value theorem, along with a short analysis of the derivative, you can actually tell whether or not you have more than one solution within an interval or not, right? Okay, now, this still does not show you any reason why the mean value theorem is important, right? That didn't really use the mean value theorem. It's kind of weird. They put these problems in this section, so. All right, so here's hopefully, my example that's going to make you believe the mean value theorem is worthwhile. All right, yes?
So, but with the mean value theorem, you can find x-intercept like that. Previous problem or no?
You could connect the two endpoints. No, that still wouldn't, no. It wouldn't give you, you still couldn't find that answer. Yeah, we'll have a way of finding it later, just not yet. Okay, so I have a thought question for us, all right? I want everyone to listen to the question carefully, think about it, and then I'm going to ask for a survey response to it, all right? So here's the problem. We have two cars. We're going to be looking from the top down at this racetrack. Here's the starting line for the two cars. We have car A, we have car B. And they're going to race down this track, and let's not even care about how long the track is. Here's the finish line. And look, this is a theoretical problem, all right? So just hear it out first, and then I'll ask you the question. Okay, here we go, right? Race is about to start. Ready, set, go. They race, right? And what I tell you is at the very end of the race, they tie. And that's why I say it's theoretical. I mean, it would probably be impossible to get a perfect tie because you could only measure it as accurate as your instrument, right? To measure, right? So let's just say in theory they started the exact same time, they race, and at the end they tie. All right? So here's the question. Is there a speed that both cars must achieve during that race? Let's just throw a number out there. Like, what I'm saying is, they drive, like, is there some speed, maybe 50 miles an hour, that they both had to have gone 50 miles an hour? So now I don't want you to be thinking 50, okay? I just want you to be thinking, is there a speed that both cars had to see on their speedometer? Is there a speed that they both have to see? Okay, that's my first question. I'll answer your questions after I finish my question. I have one more question. So the first one was, is there a speed that both cars must see on their speedometer? The next question is that speed showing up on their speedometers at the exact same moment for both cars? Okay, so any questions now about the questions?
I was just going to say the first one, it would have to be over 0 at least, which I guess is kind of, might sound dumb, but like they would have to at least see over 1.
Yeah, they would both.
Over 0.
So as this car drives, right? This car A is driving along, starts the race, and you know, whatever their speedometer says, right? And then at the very end, however fast they come across the line, their speedometer is going to say that speed, right? So at every point in time, car A has a speed. And at every point in time, car B has a speed. My first question was, is there a speed that both cars will see on their speedometers? But I forgot one big thing. We're not talking about the beginning and the end. Because at the beginning, their speed is 0, both, right? And at the end, well, the end is a little trickier, but I need to encapsulate both those problems with, I'm talking about on the inside, during the race, not at the beginning and the end. Somewhere in the race, is there a speed they both see? And the second was, is it happening at the same instant in time? Any other questions over the questions? Okay, any answers? How about to the first one? Huh?
It doesn't seem like there have to be.
That there would have to be...
Like, they'd have to have the same speed.
Are you talking about the same moment in time or just in general?
Just in general.
Just in general? So you're not quite sure they would ever both see the same speed
at the same moment in time.
At the same moment in time.
Theoretically, like A could take off at like 60 miles an hour and then stop.
Yeah. The only thing that these cars can't do is just like vanish and come back, okay? So as long as we're talking about like regular linear motion, right? Like I heard someone talking about time travel, like none of that stuff. Like these cars will, I mean, you could wait, right? Car B could take off and car A could just wait. But as long as they tie, the question is, do they have a speed that they both must see, and then is it the same point in time? So do you want to say what you think it is? Or?
Like if you just think about it like in terms of like a graph,
Mm-hmm.
right? I don't know if this will help at all. Like so if they both start at 0, like in 0 is your x-axis, right?
Okay, I'm going to draw a graph. Well, hold on. Before I draw a graph, I want to take a vote. I want to see what people think first. Okay? So how many of you think for the first question that somewhere in the race, right, both cars are going to see the same speed? It might be at different points, but there's going to be some speed that they both have to see. Okay? All right? Is that a no?
Yeah.
It's a no? So you're the only one opposed to that? Okay. Now, second vote, how many of you think that the speed that they both must see has to occur at the same point in time? You have a question?
Is that the same point in time on the track or the same point in time like...
Same point in time. Same point in time.
Okay. Gotcha.
Yeah. Same point in time. Yeah. Same point in time. So what do you think? So how many of you think that they must see the same speed at the same point in time? Affirmative? No affirmatives?
Actually, yeah.
Okay. All right, so here's the deal. This is a perfect example of a problem that is somewhat hard to figure out. And I think you could argue your case for the first and second questions. You could argue your case. And you could probably come up with a pretty good argument for whatever you think it is. But at the end of the day, it's one or the other, right? I mean, they either do see the same speed or they don't. Or they either do see the same speed at the same instant in time or they don't, right? So mathematics is here to put these sorts of things to rest for us so that we don't argue and quarrel about these things, right? Like we have a mathematical like yes or no, and that's it. There won't be any arguing, all right? There is a point in time that both cars must see the same speed, guaranteed, okay? How do I convince you of that? Or if you actually believe that, how do you convince me that's true? Yes?
The parameters here is that you have, they both reach the finish line at the same time.
They both reach the finish line at the same time.
In order for that to happen, it doesn't matter where, like, for example, car A can take off at 90 miles an hour, and car B can take off at 1 mile an hour. At some point, in order to reach at the same time, their speeds have to be the same.
Why?
Because car A will eventually, for example, in this case, car A will slow down, and then B catches up, and right just before the finish line.
Okay, here we go. I'm going to try and analyze your situation. Ready? Pay attention to the speeds of these cars.
So that one,
Hold on.
and maybe slow down there. And then maybe
Okay, so when I got to the finish line, this guy was going very slow, and this guy was going very fast.
Right.
I'm countering your... You said at the end they're going to be going the same speed.
No, I'm saying that's why I'm saying at some point they would have to actually reach the same speed at the same time in order to meet each other up at the same.
I don't know that.
What do y'all think of that argument? See, do you see what I'm saying? This is what's hard about it. It's like you can have an argument and you in your own mind can be like, this is the way it is, and someone else can have theirs and be like, no, that's not true because this scenario could happen, right? So we're going to use the mean value theorem to do it. Yes?
One thing you can do is you know that they both started at the same point and they both ended at the same point. So you have the time parameter. So
Which is the same for both.
Right.
So they both traveled the same distance over the same time. So they both have the same average speed. Which means they had to have reached that average speed at least one time. So like, think of it this way. If let's just say this was a 50-mile track and it took 1 hour, right? Then the average speed for both of these cars would be 50 miles per hour. Somewhere in the race, car A had to have looked down at the speedometer and saw 50 miles per hour. It's impossible to not travel your average speed. That's what the mean value theorem is saying. Look, the mean value theorem says, let's say this is time and this is distance. At the beginning of the race, this is just car A, all right? At the beginning of the race, car A is here, right? 0 time, 0 distance. At the end of the race, let's say 1 hour later, car A has gone 50 miles. How it got there doesn't matter. As long as it didn't vanish or do some weird stuff, it's going to be a smooth, continuous curve connecting that, right? The average speed is the secant line, right? That's your average speed. The mean value theorem says that somewhere in there, at some c, you must have your instantaneous speed be equal to your average speed. You all agree with that? That's what the mean value theorem says. That's car A. Car B has its own graph, doesn't it? So car B starts at the same place as that one, ends at the same place, but the curve's different, right? The curve is different. So I'm going to make it like really an extreme curve like this. So this car like took off very fast, covered a lot of distance in a very short period of time and then slowed down. Okay, the mean value theorem says that there is a secant line connecting these. That's your average speed of that car, which is the same as the average speed of that car. And that there's some point in time here, C, where the slope of the tangent line, the instantaneous speed, is equal to the secant. So the answer to the first question that I asked you was, is there a speed that they both have to see? And that's yes, it's their average speed. They both have to see their average speed. My second question was, are these points in time, do they have to be the same? Does this C have to occur at the exact same time that C does? And when you look at those graphs, what would you say? Probably not, but they do. Okay, and this is what I need to show you. This is what I need to show you, all right? Y'all understand this? Okay. So here's what we're going to do this. And I would never expect any student to ever come up with this, okay? This is not the point of it, okay? The point of this is to show you how you can use a theorem like this to answer a question. So what I'm going to do is this. I'm going to define two functions. Let A of t and B of t be the distance functions, or distance versus time functions for car A and B, respectively. All right? So I'm defining these two functions. So graphically, we have this. They both start at the same place, right? and they end at some point. The finish time, I don't know. We were saying 0 to 1, but let's just make that arbitrary. I'll just call it, I don't know. Let's just call it, I can use lowercase b, I guess, right? So if I were to draw this curve right here, that would be the curve I just showed you a second ago. It's going to look like something. Here's our final distance. So that's B, or sorry, that's A. And then B can be any extreme, whatever you want. I'll do it opposite this time. I'll do it like that. That's car B. Make sense? We know that the mean value theorem applies for both of those, right? We know that, but that's not the direction I'm about to go. I'm going to go somewhere else with this. Let me just write down what I want to show. I must show there exists a C in the interval 0b such that what? What am I trying to convince you of? I have to show you that there's some point in time, somewhere in here, where what? They're both going the same speed, right? Which means that what has to be the same? The tangent, the tangents, the derivatives, right, of these functions have to be equal. So I must be able to show you that there exists some C in this interval such that the derivative of the A function must be equal to the derivative of the B function at that point. Do you all agree if I can show you that this is true, I'm done? You sure? Because this is what I need. This is what I'm about to do, but I want to make sure you're convinced that this convinces you of it. I'm going to find a time between the beginning and end of the race where the speed of the A car at that time is equal to the speed of the B car at that exact same time. If I do that, I'm done. Okay, so here's how I'm going to do it. And this is the crazy cool part. I'm going to define a new function. All right? So here's my new function. I don't know what to call it. I'm going to call it W. W of t. All right? Let W of t be equal to A of t minus B of t. So what is that function doing? It's measuring the distance between the cars, between car A and car B. Right? That's a new function. So by looking at the graph right now, what would be the value of W at the beginning of the race? 0, right? What would be the value of W at the end of the race? 0. So let me draw you what W looks like. W looks like this. At 0 and at B. At 0, W is here, right? And at B, W is here. Right? Now, W in between here, I don't really even care what it looks like. What I do care about is whether or not it's continuous. Is it continuous? Why? These are both continuous because they don't vanish, the car doesn't vanish and come back, right? So these are both continuous curves. So if you subtract two continuous functions, you get a continuous function. So when I have to connect these two with a curve, right? Like that. And what does Rolle's theorem or even mean value theorem tell us there? There must be, right? There must exist a C in here such that the slope of the tangent line here is what? Equal to what? 0 because it's flat, right? So I'm going to use Rolle's theorem because I don't need mean value theorem there. By Rolle's theorem, there exists a C in the interval 0b such that what? The derivative here is what? 0. The derivative of what function? This is the W function, right? Such that the derivative of W at C is equal to 0. Right? But what is the derivative of W? Well, if I tell you W is this, right? What's the derivative of this? Well, it's the derivative of